Okay, now let's have a look at topic 12 of Introduction to Geometry, Circles and Angles. We'll divide this topic into two parts. Today, the first part, we'll talk about the concept of inscribed angles, and in our next lesson, we'll talk about part B, concepts related to angles inside and outside circles, tangents, and some more related problems. Okay, first, let's have a look at the concept of inscribed angles. So suppose we have a circle here, points P, Q, R are on that circle. We say that angle PQR is inscribed in arc PR in the diagram above because its vertex is on the circumference of the circle and its sides hit the circle at point P and R. Actually, the inscribed angles are enormously useful tools in geometry. In this lesson, we'll explore how inscribed angles are related to the arcs they cut off. So now let's consider an introductory example here. When an inscribed angle cuts off a 180-degree arc, we say that it is inscribed in a semicircle. The question is such an angle necessarily a right angle? So I'll give you 3 minutes to think about this question, and then I'll lead you through the solution, okay? Okay, any ideas? Alright, so we can make use of some isosceles triangles, right? So first of all, in triangle OBC, we know angle OBC equals angle OCB because it's an isosceles triangle, which is 1/2 of 180 degrees minus 50 degrees, right? So that's 65 degrees. Okay, we know this angle here is 65 degrees. And if you can find this angle here, then you can solve angle ABC, right? Also, we can make use of isosceles triangle OAB. Because OA equals OB, we have angle OBA equals angle OAB, which is 1/2 of 180 degrees minus 130 degrees, and this gives us 25 degrees, right? Since here this angle is 25 degrees. Therefore, we know angle ABC equals angle OBC minus angle OBA, which is 65 degrees minus 25 degrees equals 40 degrees, right? So angle ABC equals 40 degrees. Did you get it? So can you observe any pattern here? So you know that any angle inscribed in a semicircle is a right angle, which means if you consider this arc here, the angle inscribed in this semicircle is 90 degrees, which is 1/2 of this circle here, right? 90 degrees is 1/2 of 180 degrees. And if you consider this angle, if you consider this arc here, the angle inscribed this arc is here. This angle we have just calculated. This angle is 40 degrees, and it's 1/2 of the central angle here, right? Is that a coincidence, or is this angle always half of the central angle here? So let's try to prove that. So consider another question. Can you prove that if angle XYZ is inscribed in a circle such that the center of the circle O is inside triangle XYZ, then XYZ equals half of the arc XZ. Of course, XZ here is in degree measurement, not the length of XZ, but this is a corresponding degree measurement of the central angle. All right. So let's suppose X is here, Y is here, Z is here. So if you consider the arc here XZ, can you prove that this angle is always half of this central angle here? So we might use our specific cases previously as a guide, right? And we connect already to X, Y, and Z to form isosceles triangles. We don't know any angles this time, so we'll have to use variables to denote these angles. Since we know we want to use our isosceles triangles, we could let angle OYX equals X, and let angle OYZ equals Z, so that angle XYZ equals X plus Z, right? And isosceles triangles XOY and ZOY tells us that angle OXY also equals X, and angle OZY equals Z, right? Therefore, we have angle XOY equals 180 degrees minus 2x from triangle OXY, and angle ZOY equals 180 degrees minus 2z, right, from triangle OZY. We can now find angle XOZ in terms of x and z. So angle XOZ equals, we know this is 360 degrees, right? So that's 360 degrees minus angle XOY minus angle YOZ, and this gives us 2x plus 2z, which is twice of x plus z, right? So this is 2x plus z here. Therefore, we have proved the arc xz equals 2x plus z, which is twice of the angle xyz, right? Therefore, we have angle xyz equals 1/2 of the arc xz. So this angle here is always half of this angle here, the corresponding 1/2 of the corresponding central angle. Did you get it? Again, this is another important property of the inscribed angle. So let's make a summary here. So the measure of an inscribed angle is 1/2 of the measure of the arc it intercepts. For example, if we have a setup here, OPQR, O is center of the circle, PRQ are the points on that circle, we always have angle PQR is half of this angle here, POR, or half of the arc PR. Also, from this property, we can easily know that any two angles that are inscribed in the same arc are equal. For example, if we have another angle as inscribed in the same arc PR, suppose we have another angle here, then we know that this angle must equal this angle here. Did you get it? Are you clear? Alright, then let's use what we have learned so far to solve some example questions. First, consider this question here. Given that triangle ABC is inscribed in the circle as shown here, angle A equals 70 degrees and arc AC equals 130 degrees. Can you find angle C? Any ideas? Okay. Arc AC is 130 degrees. That means if suppose this is the center of the circle, then this angle here is 130 degrees, right? So if you consider the arc AC, angle B is inscribed in arc AC, right? Therefore, we know this angle must be half of this central angle here, or you could directly consider this as angle B is half of the arc AC. So that means angle B equals 1/2 times arc AC, which is half of 130 degrees, which gives us 65 degrees, right? If you know angle A, you know angle B, of course you can find angle C, which is 180 degrees minus angle A minus angle B, which is 180 degrees minus 70 degrees minus 65 degrees, right? Are you clear? Any questions? Alright, if no questions, let's consider another one. So suppose we have a diagram here. Can you find x given that angle APB equals 2x, angle ACD equals x, and arc BC equals x? Again, I'll give you 3 minutes to consider this problem, and then we'll have a look at the solution together, okay? Alright, have you finished? Let's have a look at the solution together. Okay, since angle B and angle C are inscribed in the same arc, which is AD, right? So they must be equal, since each equals half of the arc. Therefore, we know angle B equals angle C equals x, right? Also, since angle A is inscribed in arc BC here, we know that angle A must be half of that arc, which is 1/2 of arc BC, right? Which equals half of x. So that means we have solved A in terms of x, we have solved B in terms of x, we also know this angle is 2x. Therefore, we have the sum of the three angles AB and APB must equal 180 degrees, right? Therefore, we know angle A is half of x, angle B is x, and angle APB is 2x. Then we have an equation in terms of x. This solves x equals 360 over 7 degrees, right? Alright, then let's consider one last question. Chords AC and BD of a circle meet at point P as shown on the right, given AP equals PB. Can you show that AB is parallel to CD? It seems like they are parallel, right? But can you prove this? Okay, have you finished? Okay, first of all, since AP equals PB, we have angle PBA equals angle PAB, right? This angle equals this angle in that isosceles triangles. And if you consider the arc BC here, then this angle should equal this angle, right? Because angle CAB and angle CDB are inscribed in the same arc BC. So we have angle CDB equals angle CAB, right? Therefore, we know angle CDB equals CAB equals angle PBA, right? So if this angle equals this angle here, then we know AB must be parallel to CD, right? Okay, again, let's make a summary here. This is the most important property we have learned so far. The measure of an inscribed angle is 1/2 the measure of the arc it intercepts. Also, from this property, we obviously have the second property here. Any two angles that are inscribed in the same arc are also equal, right? Okay, so if you don't have any questions, let's call it off for today. Remember to complete the homework and submit them to Google Classroom before the deadline. Okay, I'll see you next time. Alright, now let's have a look at part B of topic 12. So in the second part of topic 12, we'll have a look at the concept of angles inside and outside circles, and then tangents, and we'll tackle some more related problems. Okay, first let's have a look at an introductory example. Okay, a line that intersects a circle in 2 points is called a secant. In the second part, we'll explore relationships between the angles formed by intersecting secants and the arcs of circles these angles cut off. So first, let's consider this question here. I'll give you 2 minutes to have a look at this question, and then we'll have a look at the solution together, okay? So given that AB is 40 degrees, or there's a typo here, this should be arc AB, and also arc CD is 80 degrees, can you find angle AEB? And if you finish, please give your answer in the chat box, okay? You can try to prove what we just learned about inscribed angles. Okay, let's have a look at the solution together. So for example, we could connect points A and D, right? In that case, we have created some inscribed angles. We have angle BAC equals 1/2 the corresponding arc CD, right? And this gives us 40 degrees. And on the other hand, we have angle ADB equals 1/2 of the corresponding arc, which is AB, and this gives us 20 degrees, right? You get it? Therefore, we have angle AED is 180 degrees minus angle EAD minus angle EDA. And that gives us 120 degrees, right? And therefore we have angle AEB is just 180 degrees minus angle AED, which is 60 degrees. Did you get it? Okay, so let me ask you another example. Suppose the measurement of AB is x and the measure of CD is y. Are you able to express this angle in terms of x and y? That's a connection of that angle with the corresponding arc AB and CD. So basically there's another question here. If chords QS and PR intersect at T, so suppose we have a circle, chord QS and PR intersect at some point T here. Given that the measure of RQR equals X and the measure of PS equals Y, can you find a formula for angle QTR in terms of X and Y? So the method should be the same with the previous one, right? Again, we could make use of some inscribed angles there. For example, we could connect points P and Q, right? Since angle QPR is inscribed in arc QR, we have angle QPR equals half of x, right? Similarly, we also have angle PQS equals a half of y, right? And angle QTR is actually the exterior angle of PQT, of triangle PQT, right? That means we have angle QTR equals angle PQT plus angle QPT, which is x plus y over 2. Did you get it? So that brings us a very important feature of intersecting chords, which you should remember here. The measure of the angles formed by two intersecting chords is the average of the measures of the arcs intersected by the chords. For example, in the diagram at right, we have angle PTS equals angle QTR, which equals x plus arc PS plus arc QR over 2, which equals x plus y over 2, that diagram. Okay, note here, T is not necessarily the center of that circle, okay? T could be any point inside that circle. As long as it's the point of intersection of the two chords, you always have this relationship here. Okay, please write this down, and we're going to use this to solve some example questions below, okay? Alright, have you finished? Okay, then we have a look at the point of intersection inside the circle. Now let's have a look at when the point of the intersection of the two chords is outside circle, what will happen. So here we are given a diagram. The measure of arc D is 110 degrees and arc BC is 20 degrees. Can you find angle DAE? Which basically means if you know this arc, if you know this arc, then you can express this angle in terms of these two arcs. Again, if you finish, please give me an answer in the chat box, okay? Alright, have you finished? Not that difficult, right? So we could also make use of some inscribed angles here. For example, we could connect the point B and E, right? Therefore, in that case, we have angle BEC should equal a half of arc BC, right? Which is 10 degrees. And also, the angle here, okay, first of all, we know this angle is 10 degrees. And the angle DBE is inscribed in the arc DE, right? So that equals 1/2 of the corresponding arc DE, which is 55 degrees. And also, if you consider triangle ABE, this angle here, DBE, is external angle of the angle A and angle AEB, right? Therefore, we have angle A is just angle DBE subtracted by the other angle BEC, and that gives us 45 degrees, right? So this angle here, the desired angle, is 45 degrees. Did you get it? Also, we could generalize this problem by letting BC equals X and DE equals Y and find the expression of angle A using X and Y, right? For example, if we generalize this problem like this, give it a circle like in the diagram here, XV, the measure of arc XV equals B, the measure of arc YW equals A. Again, be careful, these are arc measures, not lengths, so they are degree measurement. In the diagram, we can prove actually angle Z equals B minus A over 2, right? So the method should be the same. We can connect these 2 points, Y and V here, And first of all, we could calculate this angle here, which is A over 2, right? Because this angle is inscribed in the arc YW. And of course, this angle here is inscribed in arc XV. So that angle here is B over 2, right? And then this angle here is B over 2 minus the other angle here, A over 2, because angle XYV is the external angle of triangle VYZ of the angle Z and angle YVZ, right? Therefore, we have proved angle Z equals B minus A over 2. Did you get it? Okay, so again, this brings us another important feature. If we have two secants that meet at a point outside a circle from an angle equal to half the difference of the arcs they intercept, for example, in the diagram on the right, then we have angle Z equals B subtracted by A over 2. Okay, please write this down in a notebook. And again, next we'll use what we have learned so far to solve some example questions, okay? Alright, next let's have a look at some questions. Okay, first example, given that arc AB is 40 degrees, arc AB is 120 degrees, arc DC is 100 degrees, can you find the angle BPC and angle BEC? Again, if you finish, please give me an answer in chat box, okay? 40 degrees, 120 degrees, 100 degrees. Okay, let's have a look at the solution together. So according to what we have learned here, if you want to find this angle here, you need to know this arc and this arc, right? AD is already given to you, so the key to find angle BEC is to find arc BC. So first of all, arc BC is 360 degrees, subtracted by arc AD and arc CD and arc AB, right? And this gives us 100 degrees here. Therefore, we have, first of all, angle BEC equals arc BC plus arc AD over 2, right? Remember this? In that property here. So that gives us 70 degrees. And then angle BPC equals the difference between these two arcs over 2, right? And that gives us 30 degrees. You get it? It's very straightforward question, right? So far in this lesson, we have only learned these two properties. Okay, any questions here? If not, let's consider another example. Again, using what we have learned so far. In this figure, angle Y equals 58 degrees, angle W equals 20 degrees, segment XZ is perpendicular to segment WX. Can you find angle WOV and angle VXV? So angle V is this angle here. Oh, sorry. Angle WOV is this angle here. VXV is angle here. Find these two angles. Alright, let's have a look at the solution together. I hope you can finish by yourself, okay? Okay, first consider the angle WOV. So WOV is this angle here. In order to find that angle, we need this arc here and this arc here, right? Because this is a point of intersection between these two chords, XV and WZ. So that basically is 1/2 of the sum of these two arcs. Okay. Because we have angle XWZ equals 20 degrees, we know that arc XZ must equal twice of that angle, right? Which gives us 40 degrees. And because angle Y equals the difference between the arc WV and arc XZ divided by 2, we then have 58 degrees equals WV minus XZ is 40 degrees, right? Over 2. So that can solve arc WV is 156 degrees, right? Therefore, we have the two crucial measure of arc XZ and arc WV. So WV here is 156, XZ here is 40, right? So that means we can find angle WOV. WOV is point of intersection between the two chords, so that angle WOA should equal 1/2 of the sum of the two corresponding arcs, which is WV plus the arc XZ, right? And this gives us 1/2 of 156 degrees plus 40 degrees, and that gives us 90 degrees. That's a measure of angle WOV, right? Okay, next let's consider the angle ZXV. So we can use arc VZ here to find the angle ZXY, right? So angle ZXY is basically half of the corresponding arc because it's inscribed in the arc ZV. So we focus on the arc ZV since we know that the arc WVZ equals twice of the angle ZXW, which is 180 degrees. We have the arc VZ equals 180 degrees minus the measure of arc WV, and that gives us 24 degrees, right? Well, this arc here is 24 degrees. And therefore we know angle ZXY is simply half of the arc VZ, which gives us 12 degrees. Did you get it? Any questions? Okay, if you don't have any questions, let's take a 10 minutes break. Let's return before 35 past 8, okay? And next we'll have a look at the other two concepts, tangents, and some more related problems. So the proof we have just see here tells us very important feature. Line tangent to the circle is perpendicular to the radius drawn to the point of tangency. Conversely, a line drawn through a point on a circle that is perpendicular to that radius drawn to that point must be tangent to the circle. For example, for the diagram at right, we can write line BC is perpendicular to radius OB if and only if line BC is tangent to circle O. Also recall, this symbol here means if and only if, which means these two statements are equivalent. All right? Okay, so please write this down on your notebook, and we're going to use this to solve a series of example questions later. Alright, have you finished? Okay, let's see another example here. Line M is tangent to a circle at point A, given point B on the circle, such that arc AB is 80 degrees. Can you find the acute angle formed by chord AB at line M? So I'll draw the diagram for you here. We have a circle, and line M is tangent to the circle point at point A. So this is line M. Given point B on the circle such that AB is 80 degrees, can you find the acute angle formed by chord AB and line M? So we are trying to find this circle here. I'll give you 1 minute to think about this question, okay? And then we'll have a look at the solution together. Using what we have just learned here, we have already proved this property, so you can just use it directly, right? So if you have a tangent line here, that means we could make use of some perpendicular lines, right? I'll give a hint. So we could start by drawing the diameter AC. Then we have a 90 degrees here, right? Since we know this line is perpendicular to M at point A, and since arc AC is a semicircle, we have BC equals 180 minus arc AC, which is 100 degrees, right? So if you know the measure of the arc, of course you can find the angle inscribed in that arc. Therefore, we have angle BAC equals 1/2 of that corresponding arc, which gives us 50 degrees, right? So let's call another point Z here. Then of course you know angle DAB equals angle VAC minus angle BAC, which equals 90 degrees minus 50 degrees, and that leaves us 40 degrees, right? Did you get it? And actually, you notice that angle ZAB here is 40 degrees, which is 1/2 of the arc AB, which is 80 degrees, right? So that means if you are given, if we generalize this question as angle AB is x, then you could use the same method to find the angle VAB, which should be x over 2, right? Again, this gives us another important property here. An angle formed by a tangent and a chord with the point of tangency as the endpoint equals 1/2 of the arc intercepted by the angles. For example, in the figure at right, line M is tangent to the circle at A, which means it only passes through the circle once at point A. So here, this angle ZAB equals 1/2 of the measure of the arc AB. So if AB equals x in degree measurement, then this angle is simply x over 2. Did you get it? Again, please write this down in a notebook. This is another important property, okay? And also, an angle between a tangent and a chord is also often referred as a inscribed angle. This is the same name we give to an angle between two chords that share endpoint. Measures of both types of angles equal half the measures of the arcs they cut off. So this angle here is also called inscribed angle. Because it also equals half of the corresponding arc, right? Which means this angle. So if you have another point here, well, let's call it D. So this angle equals this angle. Both of them are called inscribed angle of arc AB. You get it? Okay, let me know if you finish, alright? Alright, good. So now we turn to angles formed by a tangent and a secant. So now let's consider another problem. In this diagram, arc BD is 110 degrees. Arc BC is 40 degrees. Line AB is tangent to the circle at point B. Can you find the angle of BAD here? So we have already learned a very similar question before, right? So if A is a intersection point between two chords like this, we know this angle should equal 1/2 of the difference between this arc and this arc, right? So here the situation is pretty similar, except we don't have two chords but a tangent line here. But the method should also be the same. So we could connect point B and D to help us solve this problem, right? So in that case, we have angle BDC equals arc BC over 2. Did you get it? BCD is here. Oh, sorry, BDC. BDC is here. That's 1/2 of the arc BC, which is 20 degrees, right? And we also have angle XBD. So let's call X is some point on the line here. Angle XBD is also a inscribed angle of the arc BD, right? So that's 1/2 of the arc BD, which gives us 55 degrees, right? And we know that angle XBD is the exterior angle of triangle ABD. So that leaves us this angle is angle BAD is simply the exterior angle XBD subtracted by angle BDC, and that's 55 degrees minus 20 degrees, which gives us 35 degrees, right? Did you get it? And again, we can also generalize this question by letting BD equals X and BC equals Y. So angle A here is, using the same method, we can prove that angle A here equals X minus Y over 2. Did you get it? So this have a similar form of what we have learned in previous property here. So if you have 2 seconds meet a point outside the circle, then angle Z here equals B minus A over 2, right? And this time we have a tangent and a secant. The conclusion is very similar. We have this property here. Again, please write this down in a notebook. The angle formed by a tangent and a secant is half of the difference of the intercepted arcs. For example, in the diagram on the right, we have angle BAD equals arc BD subtracted by arc BC over 2. Unsurprisingly, the angle formed by a tangent and a secant has the same relationship to the arcs the angle intercepts as the angle formed by 2 secants does, right? Any questions? Okay, let me know if you finish, alright? Okay, then let's consider another question. Segments PA and PB are tangent to the same circle at A and B, respectively. Can you prove that PA equals PB and that angle APB equals half of the difference of major arc AB and minor arc AB? Okay, again, let's draw a circle here. We have PA, so P is here. We have a PA touches the circle only once. PB touches the circle only once here. Can you prove PA equals PB and APB equals half of the difference of major arc AB and minor arc AB? Any ideas? Suppose this is a center point of that circle. Okay, I'll lead you through this example, okay? So we can start by drawing the ready to the points of tangency, thus forming 2 right angles. So if you connect A and O and B and O, then these 2 angles must be 90 degrees, right? We also draw PO. To complete a pair of right triangles, since we have AO equals BO, we have triangle OAP is congruent to triangle OBP by HL, right? Because they are 2 right triangles. Hypotenuse and a pair of sides. That means these 2 triangles are congruent to each other. Therefore, we have PA equals PB. This proves PA equals PB, right? And now we can find angle APB in a variety of ways. One of the methods is to use quadrilateral PAOB to note that angle APB equals 360 degrees minus angle PAO minus angle AOB, both of them are 90 degrees, then minus angle OBP, right? and that leaves us 180 degrees minus angle OBP. Angle OBP is, that should be angle AOB, because angle OAP is simply 90 degrees. Okay, and we know that angle AOB is the central angle corresponding to arc AB, so that equals 180 minus arc AYB, right? So let's suppose there's a point Y here to denote the shorter arc. We use another point to denote the longer arc. Since we know that the arc AXB equals 360 degrees minus the arc AYB, we also have the arc AXB minus the arc AYB over 2 should equal 360 degrees minus 2AYB over 2, which gives us 180 degrees minus arc AYB, right? This is exactly the same with the expression of the angle ABP. Thus, we have proved angle APB equals 1/2 of the difference of the two arcs, AXB and AYB. Did you get it? Okay, and this is you can also treat this as another property. So as shown here in this diagram at right, we can draw two tangent segments to a circle from the point outside the circle. Then these tangents are always equal to each other in length. All right. And also, we have also proved that this angle here, angle P, can be expressed as, well, suppose this is point X, this is point Y. Angle P can be expressed as 1/2 of arc AXB minus arc AYB. The difference between the longer one and the shorter one, right? All right, any questions? So the information about the angle between the tangents is unsurprising, as it's essentially the same as the angle between two secants, right? Can you connect them? This is a case of two tangents. This is a case of one tangent and one secant. And this is a case of two secants. Actually, they are very similar, right? However, the information about two tangents from the same point is new. Here, if we have two tangents like this, we can always have PA equals PB. Alright, so now let's use what we have learned so far to solve this problem here. Sorry, this one here. Any ideas? Point P is 12 centimeters from the center. O of a circle with radius 10 centimeters. Point Q is on the circle such that PQ is a tangent to that circle. Okay, let's draw the diagram. And you have a circle and a tangent line, right? So this is point O, which is center of that circle, a point P, and another point Q. So we need to find the length of PQ, right? Again, let me lead you through this. We can start by drawing a radius, because once you have a line tangent to a circle, usually we'll want to make use of some perpendicular lines, right? If PQ is tangent to that circle, we know that QO is the radius, and then this angle here must be 90 degrees, right? Then we could connect PO, that gives us a right triangle. So if P is 25 centimeters from the center, that means PO equals 25, right? And radius 10 means QO is 10. Of course, we can find PQ in that right triangle, right? So PQ is just square root of PO squared subtracted by OQ squared, right? So this gives us 225 minus 100. And that leaves us 5 square root of 21 centimeters. Did you get it? Any questions? Okay, then if no questions, let's have a look at more related problems to angles inside and outside of circle. So let's consider this question here. A quadrilateral is said to be cyclic quadrilateral if a circle can be drawn that passes through all 4 of its vertices. Can you prove that if ABCD is a cyclic quadrilateral, then angle A plus angle C is 180 degrees? So ABCD is cyclic quadrilateral, that means all of its vertices are on a circle, right? So let's draw this situation here. Suppose these are the 4 points. Can you prove angle A plus angle C equals 180 degrees? So note that angle A is the inscribed angle of the arc, the longer arc DCB here, right? You see that? And angle C is also an inscribed angle of this arc. And actually sum of these 2 arcs equals 360, right? And we know inscribed angles are just 1/2 of the corresponding arc. So we could prove this like that. We have angle A plus angle C is 1/2 of arc BCD plus 1/2 of the arc BAD, right? This leaves us 1/2 of arc BCD plus arc BAD, and then we know the sum of these 2 arcs is just 360 degrees, so that equals 180 degrees. Did you get it? Can you follow me? So actually you can also consider this as a special property for the cyclic quadrilateral, which states that quadrilateral is a cyclic quadrilateral if a circle can be drawn that passes through all 4 of its vertices. Such a quadrilateral is said to be inscribed in a circle. Opponent angles of any cyclic quadrilateral sum to 180 degrees. We have already proved this, right? Okay, so have a look at this property here. Any questions, just let me know, okay? And if you don't have any questions, let's consider another example. So consider the figure on the right. Segment PC is tangent to the circle, and segment PD bisects angle CPE. If arc CD is 70 degrees, arc DE is 50 degrees, and angle DQE is 40 degrees. Can you determine the measure of the arc from A to E that does not include point C, which is a short arc here, right? Okay, I'll give you 1 minute to think about this question, and then we'll have a look at the solution together. If you have finished, please give me your answer in the chat box, okay? Let's have a look at the solution together. So you want to find the measure of this shorter arc here, right? We know the whole circle is 360 degrees. We know this section CD, which is 70 degrees. We also know D is 50 degrees. So if you can find this arc and this arc, then using 360 minus this part, this part, this part, and this part, that'll give us the measure of AE, right? So first of all, let's see if we can find the measure of BC. First, we note that since angle DQE equals 1/2 of Q is the intersection between CE and BD, right? Then we know DQE must equal 1/2 of DE plus CB, right? So this means angle DQE is 40 degrees equals 1/2 of D is 50 degrees plus CB. So this gives us the measure of arc CB, right? Which is 30 degrees. So that solves one of the arcs we need. And now we have CB, we could find angle CPD, right? Note that angle CPD just equals 1/2 of arc CD minus arc CB, and this is 20 degrees, right? If CPD is 20 degrees, since DP bisects angle CPE, we know that angle DPE is also 20 degrees, right? Because angle DPE also equals 1/2 of arc DE minus arc AB. So that tells us that 20 degrees equals 1/2 of DE is 50 degrees minus arc AB. And we can find arc AB is actually 10 degrees, right? Therefore, we have the shorter arc AE should equal 360 degrees minus the arc CD minus the arc DE, arc CB, and arc AB, right? And we know all of these arcs, so eventually that gives us a shorter AE equals 200 degrees. Did you get it? Okay, then if you don't have any question, let's consider another question. Median AM of triangle ABC has length 8. Given that BC is 16, AB is 9. Can you find the area of triangle ABC? Okay, again, let's draw a diagram here. Median AM, we have a median here, AM has length 8, given that BC equals 16. AB equals 9. What is the area of triangle ABC? Okay, so basically we know BM is 8 and MC is also 8, right? Because M is the midpoint of BC. Any ideas? Okay, let's have a look at the solution together. So when we draw the figure and label all of our lengths, we see that BM equals MC equals AM, right? Therefore, if you centered at point M using 8 as the radius, we could actually draw a circle like this, right? A circle centered at M with radius 8 goes through all 3 vertices of triangle ABC. You see that? Then BC is actually the diameter of that circle. So we immediately know this angle here is 90 degrees, right? Because this angle is inscribed by half of the circle. Therefore, we know we could find AC first. AC equals square root of BC squared minus AB squared, and this gives us 5 square root 7. Therefore, the area of triangle ABC is 1/2 of AB times AC, and this gives us 1/2 of 9 times 5 square root 7. Did you get it? And this actually tells us one important property. If the length of a median of a triangle is half the length of the side to which it's drawn, the triangle must be a right triangle, right? Moreover, the side to which this median is drawn is the hypotenuse of the right triangle. Did you get it? Any questions? Alright, then let's consider another problem. So if we let Z be a point where the inner circle of triangle ABC meets segment AB, can you find AZ in terms of the size of triangle ABC? So basically we have a inscribed circle. Then let's draw the corresponding triangle. So these are the points of tendency. Let's call them X, Y, and Z. Okay, so can you express the length of AZ here, this length? in terms of the size of triangle ABC. Okay, let me lead you through this example. All right, so in order to facilitate our discussion, we could label the equal tangents from the vertices like this. So if we let AZ equals X, then AY must also equal X, right? Because AZ and AY are tangents of the circle. And if we label BZ equals Y, then we know this length BX is also Y. YC, if we label that as letter C, then XC also equals Z, right? Sorry, Z, not C. Then actually we want to relate X to the size of the triangle. So we write the size of the triangle in terms of X, Y, and Z. We let the size of the triangle be AB equals C, AC equals B, and let BC equals A. Then we have AB equals C equals X plus Y, right? And AC equals B, which equals X plus Z. And BC equals A, which is Y plus Z, right? We want X in terms of A, B, and C. So adding the three equations could help us with this. So add them up. Will give us X plus Y plus Z, which we can use with Y plus equals A to find X, right? So on the right side, we have X plus Y plus Z. On the left side, we have A plus B plus C. Oh, actually, the right side is twice of X plus Y plus Z, right? And then we have X plus Y plus Z equals a half of A plus B plus C, right? Then because we want to find X, so we need to eliminate Y plus Z, right? So let's call this equation number 4. So then we could use equation number 4 subtracted by equation number 3. And the left side just becomes X. The right side is 1 over 2 A plus B plus C minus A, right? And if we let, well, usually we'll use letter S to denote half of the parameter of triangle ABC, right? If we let S equals 1/2 of A plus B plus C, then we know that X equals S minus A. Did you get it? Where S is semi-parameter, or half the parameter of the triangle. So this actually gives us the relationship between X and A. Also, similarly, you can use the same method to show that Y equals S minus B, and Z is actually S minus C. Did you get it? This is the relationship between X, Y, and Z and ABC. So again, you can treat this as an important property, which states that the length from the vertices of triangle ABC to the points of tangency of its incircle are given as follows. So if you have a diagram on the right, then we have length of AZ equals AY, which is S minus A. BZ equals BX equals S minus B. And CX equals CY, which is S minus C. where AB equals C, AC equals B, and BC equals A. And the semi-perimeter of triangle ABC is S. Okay, please write this down on your notebook. And in your homework, you'll find similar questions using this property. Alright, so because we're running out of time, I'll leave 2 additional questions for you to complete as a homework, okay? So please copy these 2 questions here as part of the homework. This is the first question. And this is the second question. Alright, you could also find some more practice questions in the homework of on Google Classroom, okay? Remember to complete your homework as much as possible so we could discuss the questions in our next lesson, alright? Alright, so this is the end of today's class. I'll see you next time. Bye. Topic 13, power of a point. So in previous section, we explored the angles formed by lines that meet inside, outside, or on the circle. So in this topic, we'll explore the length of segments that meet inside or outside a circle. Together, the relationships we will prove and use in this topic are given the lofty name power of a point. So first of all, let's have a look at the meaning of power of a point by looking at this example here. Given chords A, B, and CD that meets at point X, can you prove that XA times XB equals XC times XD? Well, actually, it looks like we need to prove two ratios are equal, right? If 2 ratios are equal are desired, usually we'll use similar triangles, right? So, for example, we could connect AD and BC. Then, note that angle DAB is inscribed in arc DB. Angle DCB is also inscribed in arc BD, right? Therefore, we have angle DAB equals angle BCD, right? And similarly, this angle here, angle ADC, is inscribed in this arc. Angle CBD is also inscribed in that arc, so we have angle ADC equals angle CBA. Of course, these 2 angles are vertical angles, so angle AXD equals angle BXC, right? Therefore, we have triangle AXD must be similar to triangle CXB by AA similarity. You can use any two of the three angles, right? And therefore the corresponding sides are proportional. So we have XA over XC equals XD over XB. So express that in a product format, we have XA times XB equals XC times XD. Did you get it? So having finished with the points inside the circle, we turn to points outside the circle. So let's consider another question here. Point P is outside a given circle, and A is on circle such that PA is tangent to that circle. C and E are on circle such that secants PC and PE intersect the circle again at point B and D, respectively. Can you prove that PA squared equals PC times PB times PC also equals PD times PE? So here we can start as we did in previous problem, drawing AB and AC to make triangles, right? Since angle ACB equals half of AB and angle PAB equals half of arc AB, we have triangle PAB must be similar to triangle PCA by AA similarity, right? Therefore, we have PA over PB equals PC over PA. Of course, that gives us PA squared equals PB times PC, right? Just as there was nothing special about the course we looked at in the previous problems, there's nothing special about the secant PC here. By exactly the same reasoning, we can have PD times PE also equals PA squared, right? So we have PB times PC equals PD times PE as well. Notice that once again there's nothing special about the tangent and the secants we have chosen except that we have the point P in common. So we can put the facts we have proved in the last two problems together, this problem and this problem, in a single statement. So let's have a look at this property here. Suppose a line through a point P intersects the circle in 2 points. Pardon. Sorry. The power of a point theorem states that for all such lines, the product PU/PV is constant. We call this product the power of point P. For example, in the figure at right, applying power of a point to x with respect to the circle shown gives us XA times XB equals XC times XD. In the figure at left, the power of a point P with respect to the circle gives us PA squared equals PB times PC, which also equals PD times PE. We think of a power point whenever we have a problem involving intersecting segments and a circle. So I'll give you 1 minute to have a look at the property here, and we'll be using that to solve some example problems below. Okay, next let's consider a quick quiz. Chords Ty and OP meet at a point K such that Tk equals 2, Ky equals 16, Kp equals 2 times Ko. Can you find OP? Okay, first let's do a quick sketch to illustrate the situation here. So we have a chord Ty, another chord OP. They meet at some point K. So from the power of a point K, we have Kp times Ko equals Kt times Ky, right? Substituting the given information in this equation yields 2 times Ko times Ko equals 2 times 16, from which we find Ko equals 4, right? Therefore, we have Kp equals 2 times Ko, which equals 8. And so OP equals Ko plus Kp equals 12, right? Any questions? Okay, good. If no questions, let's consider another one. In the diagram, CB equals 9, BA equals 11, CE equals 18. Can you find the length of DE? Again, I'll give you 30 seconds to consider this problem, and after that, we'll have a look at the solution together. Alright, have you finished? Let's have a look at the solution together. So we have two intersecting seconds. So we apply power of a point, which gives us CD times CE equals CB times CA, right? Therefore, we have CD times 18 equals 9 times 20. Therefore, we have CD equals 10 and DE equals CE minus CD, which equals 8. Any questions? Okay, great. No questions. Let's have a look at another one. Points R and M trisect PS, so PR equals RM equals MS. Point U is the midpoint of PQ. TM equals 2, MQ equals 8. Can you find the length of PU? Okay, again, very straightforward question, right? Circles, chord length, and secant length. This is a typical job for power of a point theorem. The power of point M gives us MR times MS equals MT times MQ, right? We know that RM equals MS. So substitution gives us MR squared equals 2 by 8. And therefore we have MR must equal 4, right? And therefore PR equals MR equals 4. And PS equals 3 times MR, which gives us 12. Since U is the midpoint of PQ, we have PQ equals 2 times PU. Now we can apply the power point P to find PU times PQ equals PR times PS. Again, substitution gives us PU times 2PU equals 4 by 12. And this actually solves PU equals 2 square root 6, right? Any questions? Okay, good. If not, let's have a look at some more powerful point problems. So consider this problem here. These are circle O and second XZ hit the circle at Y such that XY equals 6, YZ equals 5. Given that X is 9 units from the center of this circle, can you find the area of that circle? Again, I'll give you 1 minute to consider this problem, and after that, we'll have a look at the solution together. Okay, let's have a look at the solution together. We start with a diagram. This is our circle O, some point X is here, right? XZ is the second line. Hit the circle at Y. Sorry. Y should be here. Because XY, okay, it's given that XY equals 6 and Y is equals 5. Given that X is 9 units away from the center, okay, that means we can continue segment XO to hit the circle again at some point V, and let's call this point is W. So we can use the power of point X. We have XW times XV equals XY times XZ. If you let the radius of the circle be R, substitution gives us XO minus R times XO plus R equals 6 times 6 plus 5, right? And XO equals 9. Then we have 9 minus R times 9 plus R equals 66. And therefore we can solve R squared equals 15, right? So the area of the circle O is given by pi R squared. This gives us 15 pi, right? Did you get it? Any questions? Alright, great. If no questions, let's consider another quick quiz. So as shown here in this diagram, can you find the length of BF and can you find the length of ED? Alright, have we finished? Okay, first question A, we can find BF with power of a point. FE times FB equals FA times FD, right? And therefore we have FB equals FA times FD over FE. And this gives us 20 over 3. For the second question, well, PowerPoint won't get us anywhere with ED. Our proof of PowerPoint guides us to the answer. Specifically, since we have angle FDE equals angle FBA, and we also have angle AFB equals angle EFD, right? We have triangle AFB is similar to triangle EFD. And therefore we have ED over BA equals EF over AF. Hence, EB equals EF times BA over AF, right? So that gives us 18. Any questions? Alright, good. If no questions, let's consider another one. Given that segment YD bisects angle XYZ in the diagram, right? Prove that XA equals ZB. So I'll give you 1 minute to consider this problem, and then I'll have a look at the solution together, okay? Alright, let's have a look at the solution together. So this problem involves length, angle bisector, chords, seconds, and circles. Therefore, we should consider the angle bisector theorem and power of a point theorem. The angle bisector theorem applied to angle bisector YD of triangle XYZ gives us XD over XY should equal ZD over ZY, right? This is by angle bisector theorem. However, we need something with XA and ZB. Therefore, we turn to the powers of points X and Z, which respectively gives us XA times XY equals XD times XZ and ZD times ZX equals ZB times ZY, right? Seeing some common terms in these two, along with terms from our angle bisector theorem equation, we know we are on the right track. So we solve these two equations for XA and ZB, and then we have XA equals XD times XZ over XY, and ZB equals ZD times ZX over ZY. We need only show these two expressions are equal. We have XZ in common, and we already know XD over xy equals dd over zy here. From our angle bisected theorem. So we can put this together to show xa equals xd times xz over xy, which equals xz times xd over xy. And zb equals vd times zx over zy, which gives us xz times zd over zy, right? So these two ratios are equal, xy equals xy, and therefore xa equals zb. This is how we can prove these two lengths are equal. Okay, any questions? Okay, good. If no questions, let's see another one. Point O is the center of that circle. AB is perpendicular to BC. AP equals AD, and segment AB has length twice the radius of the circle. Can you prove that AP squared equals PB times AB? Alright, let's have a look at the solution together. Since diameter BC is perpendicular to AB at point B on the circle, AB must be tangent to that circle, right? Therefore, the power of point A gives us AB squared must equal AD times AE, right? We are given AB equals twice the radius of the circle of which DE is the diameter, so we have AB equals DE. Since we are also given AD equals AP, so we have AB squared equals AD times AE, which is AD times AD plus DE, which equals AP times AP plus DE, which equals AP times AP plus AB, right? Expanding and rearranging, AB squared equals AP times AP plus AB gives us AB squared minus AP times AB equals AP squared. So you can actually factor that to AB times AB minus AP equals AP squared. So because we have AB minus AP equals PB, then we have the desired expression. PB times AB equals AP squared, right? Any questions? Okay, because of the time constraints, I'll leave the last question for you to solve after this class, okay? You can consider this as one of your homework questions. Alright, if you don't have any questions, I'll see you next time. Bye.